Hello and welcome. Thank you so much for taking the time to join us today. We are very excited to present today's webinar, Assessing Structural Vulnerability. This is a joint webinar between GKM Consultants and GeoCon. We'll be exploring strain and displacement through various case studies in structural health monitoring. For today's agenda, we will be doing some introductions on GeoCon and GKM, as well as our main presenters today. We'll discuss the main geotechnical instruments that were used on these projects, and then we'll move into a project discussion. And as I mentioned, we'll close out with a question and answer session on all the material that we cover. If you haven't joined us for a webinar before and aren't familiar with GeoCon, we were founded in 1979. We manufacture a broad range of instruments that are all made here at our factory in the US. Our main expertise is with the vibrating wire instrument that spans various product families, including piezometers, strain gauges, tilt meters, and displacement transducers, just to name a few. We employ over 150 employees, and we operate globally through a network of worldwide agents, and we also have some regional offices around the globe. A little bit about our good friends in Canada, GKM Consultants. For 17 years, GKM has helped owners, contractors, and engineering firms understand the behavior of their assets during construction and throughout their life service. In a few words, GKM offers first-class monitoring services. GKM is proud to have participated in the major development of mining and infrastructure contracts throughout Canada and internationally in more than 20 countries. GKM employs 40 professionals, engineers, and technologists. Working in the geotechnic and geostructural fields, GKM is specialized in the science of meteorology and telemetry involving various technologies. Their involvement covers a variety of project applications, mostly in the civil engineering and mining spaces. Moving on to our main presenters today. Rob Clark, the Field Services Manager at GeoCon, has more than 30 years of experience in instrumentation work. That includes instrumentation for the engineering aspects of excavations, dams, landslides, and tunnels. This includes design, installation, monitoring, and data analysis. Rob has worked with project owners to develop instrumentation contracts and documentation, and he has also worked with various contractors on documentation requests. These projects have ranged from backyard observation wells to multi-million-dollar fully automated urban tunneling programs. Vincent Lebrunier with GKM is their R&D manager. Through project experience in Canada, Mr. Lebrunier has contributed to the deployment of large monitoring projects through planning and coordinating fieldwork, providing technical guidance to subcontractors and on-site staff, installation, execution, sampling, logging, monitoring measurements, data management, and writing technical reports both in French and English. He's worked on a variety of projects in the mining industry, and he's worked on structural health monitoring projects for structures such as the Jacques-Cartier Bridge and the Alexandra Bridge. He's published papers in specialized conferences on a variety of topics pertaining to instrumentation and has offered training and classes to professionals and university students across Canada. He also has extensive experience with geophysical and geotechnical instrumentation technologies and substantial experience developing photo detection systems. That wraps up our introduction to the webinar, so we will move on to discussing the geotechnical instruments that are used on these projects. So my colleague Rob Clark will be taking over from here. Thank you.
Thank you, Joelle. It's a pleasure to join you guys today and participate in this discussion. We're mostly going to talk about a variety of different instruments that are used for structural monitoring. As you guys know, there's a large collection of types of instruments out there. We're going to focus on kind of a specialized group that are used for, like I said, monitoring structural elements. So with that, let's jump on in and let's see what kind of different instruments we're going to look at. So strain gauges are devices basically used to measure small changes of length over a fixed length, resulting from changes in force on that structural element. As strain develops within the structural element, as long as it's within the elastic range, there's a ratio between the strain and stress that's known as the modulus of elasticity. And that's also, if you know the cross-sectional element or cross-sectional area of that element, you can determine the load that's applied on that structural element. There's a variety of different types of strain gauges that can be used for monitoring, surface mount type of strain gauges or embedment type. And the strain gauges that we're going to be talking about today are surface mount. There's also a variety of different types of outputs, electrical resistance or foil type of gauges. Fiber optic is another type, but we're going to focus on vibrating wire today. So the first type of vibrating wire strain gauge we're going to discuss is the arc weldable strain gauge. This is basically about 150 millimeter long gauge that has a wire stretched within the element. It's protected by a thin steel tube, and the wire is fixed at the ends of the tube with the grips. Over the center of the tube is what's called our coil assembly. And as that coil, within the coil assembly are pluck and read coils. From the coil assembly, a signal cable goes up to a data logger or readout. At the readout, a signal is sent down to cause the plucking coil to vibrate the wire inside. And much like a guitar string that's stretched, as you change the tension on that guitar string, you get different outputs. So with the strain gauge, when that wire is stretched or compressed, you're going to get a different frequency output. And based on the calibrated information associated with it, you can determine the amount of movement associated with this instrument. So the arc weldable strain gauge, as the name implies, is typically arc welded to a steel element to measure strain in the linear axis of that instrument. The gauges, as mentioned, are 150 millimeters in length. Typical ranges associated with these strain gauges is 3,000 microstrain, but we do offer them in 5,000 and 10,000 as well. They're often, as indicated, welded to the steel surface, but if you can put them onto concrete as long as the concrete is a good quality concrete surface. Typically, it's recommended to drill holes and use epoxy grouted anchors for the endpoints. Some people will use like tabs as well to mount them on the surface of the concrete. We don't recommend that typically for long-term applications because epoxy has a tendency to creep. But if it's a short-term application, sometimes the epoxies can be used for that process. Another type of surface mount strain gauge is a spot weldable strain gauge. And this is basically a 50 millimeter long version of what was just previously described. You've got the wire stretched from one end of the gauge to the other from within the end blocks and the protective tube, and then the coil assembly over that smaller diameter tube to monitor the vibrations and the frequency of that wire. The mounting tabs for the spot weldable strain gauges are attached to the end blocks, and they're thin metal sheets basically, and you use what's called a capacitive discharge spot welder to hit each of those little circles that are shown on the screen there, those little dots. Basically, with the welder, the spot welder, creates a small indentation within the subsurface or the steel surface through that tab. And so you use that spot welder on each of those little circles, little dots, to kind of create a bond between the mounting tab and the subsurface steel surface. These are never, well, not never, but almost always used on steel surfaces for monitoring strain. These come, as mentioned, in 50 millimeter gauge lengths. The The ranges are 3,000 microstrain as well. And there's two different types. There's our model 4100 shown on the top piece there, which has a cover with a coil assembly built into the cover. So you basically mount the tabs and the steel tube with the wire inside, and then the cover goes over the top with some spot weldable straps that go over the top. The other model is the 4150 shown in the middle and the bottom, and that 4150 has the coil assembly pre-attached to the tube of the strain gauge. To protect that one, you put the basically it's a half round tubing over the 4150, and then spot weld straps, small straps over the top of those to kind of keep it in place. Again, these are mounted on steel surfaces only. Another type of instrument typically used in the structural monitoring are displacement transducers. And as the name implies, basically you're measuring changes in strain or changes in length, similar to the strain gauge, but on a little bit larger scale. And these are used for measuring like joint openings or cracks on structural elements. Basically, you're measuring the change in position from initial installed position to your subsequent current positions. A variety of different types of transducers can be used for this application. LVDTs, linear potentiometers, and of course the vibrating wire displacement transducers. Today our discussion is going to focus primarily on the vibrating wire elements. So go ahead. The first type we're going to discuss will be the vibrating wire crack meter. This is basically similar concept to the strain gauge. You've got a wire that's attached in this image here, like on the left-hand side of the fixed endpoint that extends through the transducer housing across where that coil housing is. And then there's a spring attached on the end of that wire, kind of in the center of the gauge, that extends further to the right. And that spring helps hold that wire in tension. And the springs can vary in tension depending on the range of these instruments and what they're going to be measuring. But so you've got the wire and the spring in line inside the body of that instrument to help maintain this position, and then the coil around, centered around the wire to help take the readings, create the vibrations in the wire and take the readings. These are typically mounted with groutable anchors. At the endpoints, you drill a hole into the concrete, install the groutable, or put some epoxy in the hole, install the groutable anchors, and then mount the crack meter on top of that. You could also use this expansion anchors if you have to drill smaller depth holes. Some people will use, again, mountable tabs with, if it's on a steel element, you can use weldable tabs on the end. We don't recommend, again, using epoxy if it's for long-term monitoring, but for short-term applications, we could possibly do that. The transducers, they come in a variety of different ranges. We offer them from 12.5 millimeters up to 500 millimeters. Typically with these things mounted on a structural element, it's a good idea to also provide protection, some sort of a cover, so that you can kind of minimize the thermal effects directly on the instrument. These monitor obviously the movements across joints or cracks or large openings. Another type of instrument used in structural monitoring is the tilt meter. There's a variety of different types of tilt meters on the market that basically are used to monitor the structural element's position with respect to true verticality. Some of the various types are MEMS types, like force balance accelerometers, or even vibrating wire type. The vibrating wire tilt meter is not used a whole lot anymore, but there's still a lot of projects out there that use these, and they're considered fairly reliable. They do have a limited range, that plus or minus 10 degrees is indicated. And basically what the vibrating wire tilt meter is constructed of is you've got a pendulous mass inside the vertical tube that's kind of suspended by an off-center elastic hinge. And then the vibrating wire element is in conjunction with that elastic hinge to measure the changes in verticality within the tube of that instrument. So it's very reliable, and oftentimes if there's a lot of vibrations or a fair amount of noise associated with the installation, you can install or insert some dampening fluid into the bottom of this instrument to help dampen the pendulous mass so it's not vibrating too much. These tilt meters, the vibrating wire tilt meters, are uniaxial, so they're typically mounted a couple different ways. These mounting brackets shown here are shown in plan view, and the one on the right, you would have the tilt meter, if it's just for a uniaxial measurement, you'd have it mounted on the outside leg of that angle bracket with the tilt meter kind of pointed down into the screen or the page here. For the biaxial measurement, you'd have two vibrating wire tilt meters, one on the outside vertical face shown here, and one on the lower horizontal face of the bracket. And they're both with the tilt meters kind of pointing into the page. So that provides you with the biaxial measurements. Another type of tilt meter that probably is going to be discussed a little bit today. This is the analog force balance accelerometer. This is a uniaxial device, provides good measurable results for dynamic measurements. It's fairly rugged for good outdoor applications. Temperature sensors are also a valid or reliable instrument used for monitoring structural elements. A lot of the instruments that we provide have a built-in temperature sensor with them, but if you're just trying to measure temperature only at specific locations, there's a variety of different methods to do so. You can use RTDs, fiber optic sensors, or traditional resistance type thermistor beads. The type of thermistor or temperature measurement devices that GKM provides is the thermistor type. Basically, it's a little bead that's embedded within these PVC or stainless steel housings. So you could have single nodes located at various points and provide measurements based on the resistance type of output. Or you can also have a string of these nodes attached on a single cable, either with addressable or various individual outputs for each node on a long length of cable. And the other type of instrument often used in structural monitoring is an accelerometer. These are devices used to basically measure accelerations and or vibrations. You can use the accelerometer output and through mathematical computation determine the velocity of the vibrations and even the displacement values, depending on how it's affixed to the structure. So accelerometers, such as this one shown here, typically can be used to measure, like I said, traffic vibrations, impact detection, even earthquake monitoring to some extent. They come in uniaxial, biaxial, or triaxial methods for measuring, longitudinal, lateral, and vertical displacements, vibrations, accelerations, a variety of different applications for these devices. Typically, they're mounted, fixed to the structure, like this one's shown here through that hole in the center with a bolt mounting it to the structure. You just have to make sure you align it in the direction of your anticipated measurements. And then with that, I think we're wrapping it up, and I'm going to pass it over to my friend Vincent.
Okay, so well, thank you for having me here today. What I want to do today is take these instruments and put them in the context of real large-scale projects that we've done. To do that, I want to take a step back and try to place a framework on how to think about structural health monitoring so that we all speak the same language, and then we'll see how each of these instruments fit into this framework. So the first question you need to ask yourself is why? Why would you want to do structural health monitoring? There's a whole lot of reasons, many of which are listed here. The general idea is that there's a need to identify whether the structure is behaving as intended or not. And depending on where we are in the lifespan of the structure, this may affect the choices we make in the system design. So we can more or less divide structural health monitoring in 4 large categories as a first layer. Static field testing at the top left would be you identify there's an issue with the structure, you go out, send a team with tilt meters, accelerometers, strain gauges, install them, run a test, remove the system, and then do the analysis. This assumes slow instruments with static loadings. On the top right side, you have dynamic field testing. So same idea, but this time with dynamic instruments. So accelerometers, vibration sensors, and any types of high-speed data. And I will come back to that pretty often. On the bottom left is where you would use either of these types of instruments, but you do testing as a routine part of the maintenance of the structure. So let's say every 5 years, it's planned the bridge will be closed for 3 nights, or the dam will be available for monitoring. Run your tests, do your analysis, and go back 5 years later. And then what we will be talking about today is primarily continuous monitoring. So that would be using any of these instruments and installing them permanently on the structure and running real-time analysis and validation of what the structure is doing. Then for the continuous monitoring, we can split it in several levels. Most systems will be level 1, as you can see there. It will give the basic data that engineers need to work and do their analysis. With a bit of work, a level 1 can be transformed into a level 2, where you can have a fairly good idea of where damage is located if there's any damage. And level 3 and 4 are much more advanced. To do level 3, usually you would have to have the instruments embedded in the structure from its construction, so that you know its exact baseline state, and then do your modeling from there. And level 4 would require much more advanced computing capabilities, maybe AI or neural networks, to really have a real-time status of the structure. So I've been mentioning slow static measurements versus dynamic monitoring, and this is a pretty important distinction in any monitoring system you're going to be working on. Static systems usually means any sampling rate between 1 per hour to 1 per day, more or less. Dynamic monitoring usually is anything starting at 1 sample per second to thousands of samples per second. Now you may be asking, what happens between 1 second and 1 minute? Well, that's always difficult when this comes up, because to do that transition from 1 sample per minute to 1 sample per hour requires, between 1 sample per minute to 1 sample per second requires a completely different design of the monitoring system, with different types of instruments, different types of loggers. So that's where we draw the limit at GKM there. And then once you've established that you have slow and fast measurements, you can think of your instruments as either localized or global measurements. As was mentioned in the introduction, for instance, strain gauges will give you a very specific measurement at a very specific location on a member, whether it's being under load or not. And then you have global measurements, like accelerometers. So if there's an impact at the other end of your overpass, you're probably still going to pick it up with the accelerometer, even if it's at a completely different location. And I'm not going to go over this table, but just to bring your attention to the fact that depending on the exact risk and the possible consequences, there's a whole lot of different instruments that we could be using, significantly more than the ones we will be discussing today. So with all of this out of the way, let's dive into some specific instruments and specific examples. So strain gauges, what is measured? So for strain gauges, we will be monitoring the strain on specific members or girders or parts of the structure, I-beams, whatever. Now, you're probably aware of this, but I think it bears repeating because it comes up every once in a while. From the moment we install an instrument like a strain gauge, we can only measure changes in strain from that point on. We cannot go back in time and know the strain, the changes in strain from the construction of the structure. So that's something to keep in mind. Another thing is that it does not give us a direct measurement of stress, which is actually what we may be looking for. If we have a good knowledge of the structure, we know how it behaves, we can have a pretty good guess at what the stress is, but we don't have a direct measurement of it. And as mentioned earlier, they can be surface mounted, embedded, etc. We're going to be talking about surface mounted strain gauges here. On the left, there is the vibrating wire strain gauge. So it's very durable, very stable in time. So for any sort of long-term monitoring, it's usually the preferred choice. But they do have a slow response. And while it's possible to read them dynamically, it's more difficult. It takes specialized hardware to do. On the right-hand side, there's an example of a foil strain gauge by BDI that is completely packaged in a protective enclosure. So foil strain gauges have a very fast response, they're very sensitive, but they can drift over time. So if you're looking at doing long-term monitoring, you can't really rely on that. To an extent, it's even recommended to reset it, so to bring it back to zero regularly and only use it for dynamic events and assume that and only measure changes during that dynamic events. So this is an example from a project we worked on in Eastern Canada. So this is a highway overpass. There are 11 concrete girders that are not in the best of shapes, as you can see there. So we went in and installed vibrating wire strain gauges there. Obviously, it's a concrete structure, so we used drop-in anchors, grouted anchors, sorry, and they were attached to the blocks like this. You may be wondering why 3 strain gauges like this. The reason is that we knew we wouldn't have uniaxial loading, and this gives us a quite direct measurement of shear in addition to axial loading. This is a view of the installation when it's completed. So there you can see that we had all the instrument cables run into PVC pipes to protect them from the environment and make the structure look better. You can also see, well, you can't really see them here, but there were also crack meters, displacement transducers installed mid-span on the girders to measure their full deflection. And it's kind of small, but on the left, you can see, just give me a second here. On the left there, you can see the solar panel that is used to power the system. So in this case, we were asked to do fast measurements, 20 samples per second. There were a few reasons for that. The main reason is that the overpass owner wanted to do live tests with known loads. So they needed to see exactly how each girder behaved while a known load was traveling over the overpass. And also they have really good traffic statistics. So we did 4 bursts of high-speed data per day, and they could track how the bursts changed over time. In addition to that, since it's a fast measurement, we can also decide to take slow readings every once in a while. And this is better for long-term monitoring to do it like this and have both in the same system. However, because we need the fast measurements and we need to collect data in real time from dozens of instruments, everything has to be fully wired. I'll get back to that in a few minutes. This is another example from a bridge, a steel truss bridge, still in Eastern Canada, where you can see we had these vibrating wire strain gauges installed in specific locations, about 70 of them, and as well with a few resistive or foil strain gauges in a few locations. So you can see that they were all installed under covers with anti-rust, rust-proofing, paint. In this case, was not deemed necessary to run the cables into conduits, but all the cables are nicely strapped to the structure all the way back to the data acquisition system. So more views of the same types of instruments. This is a typical data acquisition system for a project like this, where we have high-speed interfaces reading from instruments. So the idea is that all these interfaces run in parallel. They all run at the same time. So instruments are synchronized, and it allows for much more powerful analysis of fast readings because we know how every instrument is related. And on the right, for that highway overpass, we also added an external enclosure with manual switches that they could use to trigger fast readings during their live tests without having to climb all the way up there and connect with specialized software to the logger. So that was an easy way for them to run live tests. So quick summary on strain gauges. They're very versatile. They can very easily target problem sections or parts. One con is that it can be expensive to cover an entire structure with them. If you want to install 200, then you may need to run 200 separate cables along the structure. This is very time consuming, and bridge owners typically don't want to close their bridges for days for this kind of operation. So something to keep in mind. I'm not going to have the time to go into every detail or for every of these questions. So if anybody wants me to go into more details, you can add questions to the chat. Temperature effects are very important to take into account. Strain gauges failures happen sometimes. It's pretty rare. Usually it's either ice or mechanical damage of some sort. So it's not the gauge's fault, but it's just due to the environment. Rust from the structure can be an issue in some kinds, so something to be careful about. And as mentioned, some types of instruments can drift. Tilt meters, not going to spend too much time on that. Measure changes in tilt. A lot of different things can change tilts of the structure. So it's an indirect measurement in a lot of cases, but it can be very sensitive to changes in the structures, in the footing, differential settlement. So on the left, on a steel truss bridge, you can see a force balance accelerometer. It's very sensitive, but in theory, it can drift over time. So it may be necessary to replace them. So this means you need to have a plan with backup instruments and scheduled maintenance to go and replace them, send them to be calibrated, etc. On the right, there's an example of a vibrating wire tilt meter attached to a spillway. I'll come back to this in a few minutes. Crack meters, at a very basic level, a crack meter and a strain gauge is a very similar type of instrument. They measure changes in position between 2 points. So we may use them across dilation joints, near footings, across blocks. It's a pretty direct measurement, and it's complementary, let's say, to tilt or strain measurements. So here's an example. This is a locks. It's still in Eastern Canada, where this structure is in the middle of the canal near the locks, and there's a crack running the entire length. So major crack, we put in crack meters, and we did fast measurements here because we wanted to see what if the crack responded to any of the events that would typically occur on the structure. So could be the bridge going up and down, could be railway traffic, could be vessel impacts, etc. And we also wanted to be able to do slow measurements. Now, this didn't go quite as planned. We were not able to properly identify each type of events, or at least that the crack responded to these events. So now the system works as a long-term monitoring of any changes in the crack over time. This is a spillway infrastructure in central Canada. So on the left, there is a tilt meter there. On the right, there is a bunch of there's a triaxial crack meter. So to measure opening, differential settlement, and movement in and out of the plane. Now, in this system, it's a spillway. It's not actively used. The water level is pretty stable. So there was no reason for us to do dynamic monitoring there. Measurements like 3 or 4 times a day is more than enough for what we're trying to measure over long periods of time. So in this case, using a completely wireless and battery-powered system makes a lot more sense, because you save a lot of manpower on installation, and these systems also tend to be less expensive than dynamic monitoring system. So if we take a step back, we can see the instruments in the bottom left there, and the instrument cables just run to this battery-powered enclosure there. And if we take even more steps back, we can see that there is the data logger here with internet connectivity in there. And along the structure and across the water, we have the instruments with their radio loggers sending their measurements back with the antenna there to the internet-enabled station there. So we can see that the instruments were very stable over long periods of time. Same for the tilt meters. There were a few hiccups with some of the temperature sensors, but was not a big deal for this project. So temperature sensors. So all the instruments we mentioned so far contain a temperature sensor, but in some cases we may need to add more. And the reason is that temperature affects the structure. So if the sun is shining on one side, that side's going to get hotter, it's going to try to dilate, then the other side will not dilate as much. And structures like dams and bridge are designed take that into account and to have some flexibility in the structure. That being said, older structures like the first steel truss bridge I mentioned has become very stiff over time. So any changes in temperature can add a lot of stress on individual members, and having a complete picture of the temperature distribution is necessary to do all the analysis of the strain measurements. Accelerometers. This is my last instrument type for today. So accelerometers is a bit on its own. It's a different family of instruments, different type of analysis, but it's still very commonly found in structural health monitoring. We can measure several things with it, such as the natural modes, vibration from weather events, from blasting, etc. And I'll give you 2 examples. This is for a LOX infrastructure still in Canada. And in this case, we have installed accelerometers to detect vessel impacts, because there is damage that was being observed on the structure, but they didn't know exactly where it came from. And one of the hypotheses was that it came from vessels either hitting the walls or scraping the walls of the structure. We did that monitoring for about 6 months, and over 6 months we detected maybe 7 impacts, and they were not very strong. So the structure owner may have to look somewhere else for where the damage comes from. This is an example of one such event. So future steps of that project would be to have a camera on site, or have the monitoring system be able to interface with the surveillance system they have and automatically pull images from vessels, from the cameras, if any such event is detected. But this can only be done really with accelerometers. And then if we've properly established that events such as this are rare, then it may be necessary to install other instruments like strain gauges, tilt meters, to perform long-term monitoring of the structure to make sure it's not just degrading on its own. Second example of another type of measurement that can only be done with accelerometers was on the second steel truss bridge I mentioned. We were able to monitor the modes of the structure. So we can measure that the structure vibrates in very specific ways that were in line with the modeling from the structural engineer. So this for a steel truss bridge turns out that it may not be sensitive enough. Like it takes a lot of damage for these peaks to shift significantly. But it was a trial project from the bridge owner. But for cable stayed bridge, it's a very sensitive measurement. Any change in tension on the cable stays can have a huge impact on the position of these frequency peaks. So accelerometers themselves are well understood. If you know how to use them, you can get a lot of information of them, but they require large sets of data, and they require specialized software analysis mathematics to get the most out of them. So same types of instruments can give different types of information depending on their acquisition frequency, if it's going to be for single tests or long-term monitoring, etc. In addition to this, there are other global methods that can be used that are becoming more and more popular, such as NSAR. So this is measurements from satellites that measure elevation of the ground or of the structure. Automated total station to track the position of prisms on the structure. GPS receivers on the structure to track their position very accurately over time. So it's a whole wide world out there, lots of options, keep your mind open. And for the future, well, the hardware is pretty mature. The future is probably in modeling, AI, digital twins, these kind of things. So this is something you will be hearing more and more about, especially for newly built structures. So that was my time for today. If you have any questions, Joel will be able to share them with us. Thank you very much.
Thank you, Vincent. So looking at questions, we have one here. Are these instruments capable of being submerged in water? Thinking of an application where there's a crack present in a concrete dam or similar structure.
Rob, want to take it?
Yeah. So yes, these instruments like crack meters or strain gauges are designed to be submerged. It depends on the quality of the water, though. If it's seawater, there's going to be a fair amount of corrosion, and the crack gauges or strain gauges can be built to withstand those kind of environmental impacts on those. But if it's just fresh water and they're going to be completely submerged for extended periods of time, a standard instrument should probably be more than sufficient.
Great. All right, let's see here. Is there a way to measure stress directly? Vincent, do you want to grab that?
Sure. On some structures, like concrete dams, it's possible in theory, but it's a difficult type of test to run. It's a specific type of instruments that GeoCon provides. I don't remember the exact part number, but basically you have to insert the instrument in the concrete structure, then overcore and retrieve the overcoring and see how much it relaxes. It's a very specialized measurements, and it's probably the only way to do it after the fact. For cable stays, to an extent it's possible during bridge construction to add a load cell to some of the cable stays, but after the fact it's nearly impossible to do.
Thank you, Vincent. What would be some good ways to protect the sensors from ice or from rusting? Would you like to grab that one, Rob?
Well, I mean, you have to prepare the surface for rusting. You need to prepare the surface as best as you can. And Vincent can probably speak to this as well. You want to make sure that that surface is clean of any corrosion when you do the installation. And then afterwards, you want to, once you install it, you want to protect that gauge from further corrosion. So, you know, mastic over the installation, whatever, you know, primer paint, some sort of epoxy paint, something that'll seal it up and protect it from additional corrosion. Vincent probably add to that for.
Yeah, so something that's happened on the first steel truss bridge I mentioned is that it's very old carbon steel, so it's more prone to rust than modern steel. And even if we did all of what Rob said, what ended up happening there is that the steel surface would still rust under the cover, and then there would be dust or flakes that would detach, and it would still be magnetic enough that it would interact with the coil from the sensor. And this would still give us readings, but they were all wrong. And to be honest, took us a while to figure out what was going on. You know, over 5 years, it happened like 4 or 5 times out of 70 something sensors, but you know, it's something you have to be aware of.
So you're saying just replace the bridge?
Yeah, I guess, but that's not my call to make, really.
How do you see the future of instrumentation and infrastructure, and are we prepared for it?
Well, this is a really broad question, and it's to an extent a matter of culture more than anything else. So if the governments, regulatory bodies decide to include monitoring right off the bat in their bid proposals, this ensures that monitoring will be continuing for a long time, and we'll have large data sets that we can use to train neural networks and other types of models. And I think overall this is where we're heading. As I said, the hardware is pretty mature. There are still improvements being made for wireless data transmission, and sensors are more reliable than they used to be, even just 10 years ago. But we may be hitting a plateau there eventually. Anything you'd like to add, Rob?
No, I think you kind of nailed it there. I think over the years, there has been more requirement in contract documents for monitoring as a result of, litigation and kind of CYA processes. So I think that's kind of an important aspect of many projects nowadays is to have the monitoring in place to not only evaluate what's going on during construction, but to make sure that there's no damage to that construction activity or the surrounding environment. And like you said, there's advancements going on in technology with how things are being monitored. You mentioned INSAR. INSAR is a great resource for providing some global monitoring in expansive areas, and you can go back in time with INSAR now, and you don't necessarily have to start from where you set it up. There's records available through INSAR of conditions several years back, so you can go back in time to see what's going on and then move forward with your monitoring. So lots of great technology out there, pretty cool stuff going on.
Excellent. We have one asking, are AI instruments reliable? I suppose that would depend on any of our experience with AI instruments thus far. If you have any comment on that.
Yeah, I do. This is a can of worms that I don't really want to open. It's not, it really depends on how the legislation surrounding engineers is set up in your area. In a lot of cases, at least where I'm from, the engineers have to be able to redo the maths themselves, and lots of AI models are black boxes. So at the moment, it's kind of an issue still. I can't name names, but I know of large engineering firms that have departments working on that specifically. But it's not ready yet to be used for real-time monitoring, but I'm sure it will be within 5 or 10 years.
Great. All right, we will wrap up the question session with that one. Thank you very much, Vincent and Rob. So to close out today, we'll just go over some of our contact information for both organizations. So for GKM, we have our sales team. They can help you with any quoting or ordering requests. We do have a technical support group as well. They can provide installation support with configuration and troubleshooting. And then we also have training here at GKM that's both virtual and in person. So that's your hardware, product, and installation training, as well as software configuration. And for GKM, they have their sales team there. Their main headquarters in Montreal, Canada. GKM is GeoCon's authorized agent in Canada. So if you're located in Canada, have a project going on, and you need some GeoCon equipment, you can feel free to reach out to the sales team at GKM directly. And they can help you out with a request on GeoCon equipment or any of their other services that we've discussed or that they have listed here in terms of consulting and installation, and any other customized solutions that you might need for any variation of projects as they have listed right here on this slide. So thank you once again for taking the time to join us today for our webinar on assessing structures. And we hope that you have a good evening or morning wherever you are in the world. Thank you so much. Bye.